right, class, let's get started with carboxylic acid derivatives. So in chapter 20, we talked about how you can use your carboxylic acid and nitriles, which is a last level of oxidation, how you can get those from your carbonyl compounds, a simple oxidation, because aldehydes and ketones, they are extremely reactive. So if you have, for example, benzaldehyde, you could oxidize it just by air even. That was one of the things I said. But that will not be a high yielding reaction, keep in mind. So if you're doing a prepare question, don't put on air. You want to seek a good reagent for that. It'll take you forever for that reaction to take place. All right, so typical oxidizing agents, if you recall, we had Tollen's reagent. Of course, you can do your KMNO4. You can do your Jones reagent. All of those, they are fantastic reagents for this transformation to take place. In this particular chapter, we are going to dig deeper into what are the various different kind of carboxylic acid derivatives. So how can I functionalize my carboxylic acid into perhaps an ester? Or what could I do to get it into an anhydride or an amide for that matter? All of those, or acid chloride, all of those are going to be discovered in this chapter. That's why we use the word carboxylic acid derivatives to describe each of those, to club each of those together. So to give you a flavor of that, I want to take you back to something you have learned in Organic 1, and that is that if you have an acyl group bonded to some electronegative element, the difference between an acyl group bonded to an electronegative element, in which case we call it a carboxyl, as against when it is bonded to another carbon or a hydrogen, in which you use the word carbonyl to describe that. So the moment you use the word carbonyl, you're thinking about aldehydes and ketones. The moment you use the word carboxyl, automatically you're thinking that your acyl group, your C double bond O, is connected to some kind of an X, some kind of an electronegative element, which is going to be something like a nitrogen in case of an amide, a halogen in case of acid chlorides, an oxygen in case of the carboxylic acid and the ester, could be a thioester, so on and so forth. So let's take a look at some of the ones that we will talk about in this chapter, and I will highlight when the time comes for the ones that you may see in your biochemistry course. So we have talked about carboxylic acids, of course, in chapter 20. We will learn how to generate acid halides from the carboxylic acids. We will also learn how to convert either an acid chloride, or starting from the carboxylic acid, how could you generate an anhydride. Esters, those are the sweet smelling carboxylic acid analogs. Amides, those are present in your proteins. So each amino acid tags on to another amino acid to form a protein. If you've taken the first level of biology, General Biology 1, BSc 1010, you would have talked about, your teacher would have talked about how the peptide bond, as they call it, or the CONH bond, which is basically an amide bond. So we are going to take a look at that. Thioesters, these are just a little stinkier cousins, as you would imagine, because instead of using an alcohol, you would use a thiol to synthesize these thioesters. And then, of course, the phosphates. Basically, you have the phosphates that are present in your ATP. Not in an acyl form, but in biological systems, you would see a lot of the acyl phosphates. So typically, you would come across the thioesters and the acyl phosphates in your biochem course, but we'll still take a brief look at that as to how or where they belong. So I want to get your attention to the Y group again, and I want to go over how this Y group, which is an electronegative atom or a group, would be able to behave differently than what you have seen in the past. So for example, if I compare this to a carbonyl group, let's use an aldehyde, perhaps an yeah, let's just keep a generic aldehyde. And maybe I'm bringing in a nucleophile, depending on whether it's negatively charged or whether it's it's neutral. It's going to behave just that bit differently. The nucleophile attacks the electrophilic carbon. Electrons move on top of oxygen. We have seen that you would have the sp3 hybridized intermediate. And so depending on whether it was a neutral nucleophile or whether it was a negatively charged and what the reaction conditions were, maybe it was aqueous, it's going to borrow that proton and it's going to either form the OH, the nucleophile still connected. So this is a common reaction. For example, recall the cyanohydrin, for example, or the hydrate formation. And then we also spent time talking about the neutral nucleophiles. Maybe you have like methanol or ammonium that is getting added, which is going to form the iminium ion. And in that case, following the similar route, there is, in the last step, there is a loss of water, and so you end up with an NH, which is what we called aldimine. Right? So we talked about that in chapter 19, two different case scenarios, but that is going to be very different as compared to the reaction that you see in case of a carboxylic acid derivative. So you have your nucleophile that's going to attack your electrophilic carbon. Electrons are going to move on top of oxygen, which is what I'm showing you here. When the electrons come back, so when you draw out, I mean, at this point of time, you should be using your notebook and using the time to take the time to bring over the arrows so you start getting used to that when we put it in practice on an actual molecule. And now when the negative charge comes in, you would have the loss of the leaving group, and that will generate your C double bond O is back. You have substituted the nucleophile in place of where Y was. So the leaving group has left and the nucleophile is sitting in its position. Let's take a look at naming various different carboxylic acid derivatives, and the first one we'll talk about is the acid halide. This is a derivative of the carboxylic acid. So what we are going to do is we are going to drop the ic acid part of the carboxylic acid, and if it's the full word carboxylic acid, we will just drop the whole part carboxylic acid. We will replace the ic acid by oil halide. So if it's a chlorine group, we'll call it a chloride, bromide, iodide, and so on and so forth. For example, the given structure contains 2 carbon atoms. That means it must have come from acetic acid. So I'm going to drop the ic acid and I'm going to replace it with il halide. So the name becomes acetyl chloride. You might want to consider the IUPAC name for that. So we would have called it ethanoic acid. Again, I'll drop the ic acid. The name becomes ethanoyl chloride. There is a space in between. Likewise, if you look at the next one, that is coming from benzoic acid. This is benzoic acid. I'm going to drop the ic acid and replace it with the Br, right? So I'm going to drop it and call it benzoyl bromide this time. So again, oil, OYL, is how you would end it, because you drop the IC and then the acid that was replaced with YL and then the name of the halogen atom. The last one that you see here, if it was a carboxylic acid, you would have just called it cyclohexane carboxylic acid, right? This was cyclohexane, carboxylic acid. So we are going to drop the carboxylic acid part. We'll retain the cyclohexane. We will call this part carbonyl chloride. So if it was chlorine, bromine, iodine, they will become chloride, bromide, iodide, fluoride for fluorine, and so on and so forth. Let's see if we are able to put this together on some practice. So propionyl, that comes from propionic acid. Prop means 3 carbon. So that's what you should have. That's the propionic acid. We want to generate the acid halide out of it. So the CH3CO part remains the same. But since it's a bromide, I'm going to say it's a COBr. 1, 2, 3. That is the propionyl part. Prop means 3 carbons. And the ill bromide says that it tells you it's a terminal functionality which contains the COBr unit. And it's stemming from the corresponding propionic acid or propanoic acid. Propanoic acid. So I would say the propionyl bromide is the more chemical abstract Ca name. On the other hand, if you wanted to give it a name which is a more IUPAC name, that should be propanoyl bromide. Just know the difference between propionyl and a propanoyl. Yeah. Benzoyl chloride, very similar to the benzoyl bromide that we just did a couple minutes ago. We have the benzoic acid as the parent carboxylic acid, and we are just converting that into a COCl, right? We did COBr previously. If you were to look at the third one at this point of time, I would encourage you to pause me and then compare your answer with mine. The starting point for numbering should be the COCl, the carbon attached to that. So that's position 1. That means this is the cyclopentane. It's the kind of cyclopentane, the second position and the third position of which holds the methyl. There is no cis or trans that has been marked, so we'll just call it 2,3-dimethyl. We call it 2,3-dimethyl carbonyl. So the COCl contains this carbonyl and the chlorine, right? So the full name becomes 2,3-dimethyl cyclopentane carbonyl chloride. And if you look at the last one, we have over here the COBr. You're starting to number at the terminal functionality 3, 4, and 5. So it's going to stem from pentanoic acid. And it's okay when you're just starting out to just write down the carboxylic acid, but make sure that you strike through, right? And you put in the YL and then the bromide. So the name becomes pentanoyl bromide. So YL and then the name of the halide is how you're going to name it. All right, let's take a look at the acid anhydride. We have the benzene ring, which is connected to a C double bond O. That is connected to another oxygen, another C double bond O, and then there is some aliphatic or could be aromatic chain. So this unit that you're seeing is called as the anhydride unit. Recall from your organic 1. Just like ethers, anhydrides can be symmetric or asymmetric. So we said ethers were COC, these were ethers, and then depending on whether these groups were exactly the same or different, we called it symmetrical ether or asymmetrical ether, right? Just like that, your anhydrides are also or could also be symmetric or asymmetric, and it's the same idea. that if the R and R prime are exactly the same, we will call them symmetric anhydride this time, because this is an anhydride group. And if they were not the same, we will call it an asymmetric anhydride. Sound good? All right. So in order to name it, all you got to do is get the name of the carboxylic acid. So the name of the carboxylic acid it's stemming from is benzoic acid. It's also stemming from acetic acid. And then the word anhydride to describe the functionality is there. So acetic, benzoic, anhydride. Now you may say, why did acetic come prior to benzoic? The reason for that is just alphabetizing, nothing bigger than that. What that means is that if you wanted to, tomorrow, if you wanted to put this as a completely IUPAC name, you will have to call it benzoic ethanoic anhydride, because your two acids would then be benzoic acid and ethanoic acid for acetic acid. So know the difference between the CA and the IUPAC name. Okay, so we have butyric anhydride. The fact that there is only one ic acid in the front, that should tell you that this must be a symmetric anhydride. So symmetric anhydrides, for example, acetic anhydride, right? So that would mean that it only has acetic acid on both the sides. So you can, there's two ways to see this. One is that you can put down the anhydride first and then extend on both the sides. It says butyric. So you're not going to call it dibutyric, by the way. 1, 2, 3, and 4. Just butyric. So 1, 2, 3, and 4. That should be the structure of butyric anhydride. Butyric anhydride stems from butyric acid, which is rancid butter, which is also butanoic in the IUPAC system. So you could call it butanoic anhydride as well. If you look at the next one, we are calling it acetic formic anhydride. So anhydride, let's draw that out. And that's a terminal functionality as well. So I have marked my 2 carbon atoms. On one hand, I want to put it acetic because that means 2 carbon chain. Formic means 1 carbon chain. So this is a 2 carbon chain. This is 1 carbon chain. That should be the structure of acetic formic anhydride. Notice I used the acetic and the formic together. So both of the CA names were taken together. I could make it truly IUPAC and I could totally call that ethanoic, methanoic anhydride. And that's okay too, because some of the names, like we have discussed, especially in the carboxylic acid world and the derivatives, which you will see in biological systems, and they continue to use the CA names more commonly. So let's take a look at the next one. We have 1, 2, 3, 4, 5, and 6. This must come from hexanoic acid. We have only 2 carbons on the other side, so that must be ethanoic. We are going to put these together to reflect our name. So it could be ethanoic, hexanoic anhydride as the proper IUPAC name. Let's take a look at the last one. Again, we are going to go ahead and mark the carboxylic acid. This is coming from a propanoic acid, right? And this part is, anybody? It's not benzoic. It is not benzoic. This is cyclohexane carboxylic. This is cyclohexane carboxylic. And so you will just basically put those together in an alphabetical manner. So cyclohexane carboxylic, propanoic anhydride. All right, let's then discuss the amides. We have the amides again, which are carboxylic acid derivatives. We have replaced the OH by NH2. sometimes these could be NHR, and occasionally there might be NR2. And these could be two different R groups, so R and R prime, that's a possibility. So let's take a look at what is a primary, secondary, and tertiary amide. First things first, we are going to replace the ic acid, right? So it stems from acetic acid. I'm going to replace the ic acid by the whole word amide. So acetic acid became acetamide together, one word. Hexanoic acid, 1, 2, 3, 4, 5, and 6. It must have come from hexanoic acid. I drop the oic acid part and replace it with the full word amide, one word, hexanamide. Notice this would have come from cyclohexane, carboxylic acid, right? And we are going to drop the whole word carboxylic acid and going to put down carboxamide in place of that. Notice what I have going on at the bottom panel. I have on the nitrogen, so the top three that I have showed you, they were connected to only one carbon atom. That is why we call those the primary amides. These are all primary amides. So the only one carbon atom that they were connected to was the acyl carbon. Yes. If you look at the second one, I have one bond going to the acyl group. I have one bond going to an alkyl group. So this is something which would have gotten formed as we go forward. You will know it will need a primary amine for the reaction to take place rather than ammonia, for instance. So here you do have this methyl group that needs to be defined. If you don't, then you would, following what we have so far, you would say, well, this looks like a propanamide, right? But what tells propanamide, which is fine, but how do you know that this was formed from a primary amine or is a secondary amide? So I'm going to call it a secondary amide because it is connected to one bond, two bonds going to carbon atoms. So I'm going to call it a secondary amide. And notice the use of the N. I'm going to call it N-methyl in order to signify that this methyl group is connected to your nitrogen atom. So the name becomes N-methyl propanamide. If you look at the next one, I have over here a cyclohexane. I have a cyclohexane which is connected to an acyl group, so that will be cyclohexane carboxamide. This is a tertiary amide, and I call it tertiary because you have one carbon, second carbon, and third carbon. So this is a cyclohexane carboxamide, and since the nitrogen contained two ethyl groups, I'm not going to call it N-ethyl. I'm just going to call it N-N-diethyl cyclohexane carboxamide. You got it. Let's see if we can work on some of these. It says it's supposed to be heptanamide. Hepta means 7 carbons. So let's draw out the root name first. So you have 1, 2, 3, 4, 5, 6, and 7 terminal positions. So that's going to be your amide. It doesn't say NN. That means it must be a primary amine. And so you have over here, that's position 1. Position 3 contains an ethyl group. Position 4 contains an isopropyl group. Position 3 also contains a methyl group. You could have drawn it like that so it still looks like a tetrahedral. Or you could show That's a CONH2. 3, 4, 5, 6, and 7. Fourth has the isopropyl, ethyl and methyl. You could show it like that too. So rules that you have learned in Organic Chemistry 1 to draw your structures still hold true. Again, always go with the root name first and then follow it with the substituents rather than the other way around. Cyclohexane carboxamide means that you must have a cyclohexane, and directly connected to that is a amide bond. But here it says that it's supposed to be N-ethyl N-methyl. That means it is it's a tertiary amide. It is not a primary amide. So I will have to make some adjustments. So I remove my H2. I'm going to put on that nitrogen a methyl group and an ethyl group. Notice the difference between this and the previous example, which was NN diethyl. In that, we had suggested that the two R groups were exactly the same. Here we are saying that the two R groups, one of them is an ethyl group, the other is a methyl group. Hence, we have to write it as N-ethyl N-methyl. Notice the use of alphabetization for the E versus the M, cyclohexane carboxamide. And if you look at the last one, you're still going to follow the lead that this is going to be some kind of a pentanamide. The third position of which contains the bromine group. So that becomes 3-bromo-pentanamide. Let's take a look. What would it be if I were to draw out, perhaps I have a CONH, so C double bond O, on the nitrogen. Perhaps I have a methyl, maybe I have an ethyl group, and I have this chain going, and perhaps one of the locations has a methyl group too. So how would you name this tertiary amide, which has some groups that are common on nitrogen as well as the rest of the chain? You would still go ahead and number the chain. So that is propanamide. It's the kind of propanamide in which the nitrogen has a methyl group, and so does the position 2. So you would want to say that. So that will be N-2 dimethyl, because you want to consolidate. And then the ethyl group is present on nitrogen as well. So we will use the word ethyl as well. So the name becomes N-ethyl N-2 dash dimethyl propanamide. Likewise, if you had perhaps maybe a butyl chain, you have a C double bond O, you have a nitrogen, you have an ethyl, maybe this one is secondary, and I have an ethyl group here, maybe I have a benzene ring. Let's make it fancy looking. And so how would you name that? So starting again, your amide is going to be your point to begin with. That's your terminal. You'll consider that a terminal functionality. That will be 1, 2, 3. So this is some kind of a propanamide still, propanamide, where the third position has the phenyl and your nitrogen, and the second position, so N-2, have the diethyl. So N2 diethyl dash 3-phenyl propanamide will be your answer. Okay, let's go forward. Let's take a look at the esters. So esters are a little bit different than your amides, because amides will have this potential that they can be primary, secondary, tertiary, because nitrogen can have NH2, NHR, and NR2 type of a system. In case of an ester, your oxygen is happy with just 2 bonds, right? So if you have a C double bond O and that goes to a carbon, we call it an ester. If that goes to a hydrogen, we call it the carboxylic acid. So at any given point of time, you do not have a scenario where oxygen is making 3 bonds, not possible. So there's only, and each of these is a different functionality. So you don't have to worry about a possibility such as you did in case of the nitrogen, that you had to specify what follows the nitrogen. So you never will say, for instance, in case of naming this, we've seen part of this before, you have to replace the ic acid by 8. So for example, this is coming from 1, 2. It's coming from acetic acid. I'm going to replace the ic acid by 8. That is why it became acetate. And I would put the prefix as to what follows oxygen. What is the alcoholic part of the ester? And that contains 2 carbons. So I'm going to call it ethyl acetate. Notice I'm not calling it O-ethyl acetate. That will be redundant. So just ethyl acetate, right? You could, if you wanted to, call it ethyl ethanoate. That's okay. That's acceptable. And the reason why it's acceptable is because it's stemming from ethanoic acid. So I replaced the ic acid by 8, so the name became ethyl ethanoate, and that will be the complete IUPAC name for this compound. Let's take a look at another one. We have over here 1, 2, 3. It's a dicarboxylic acid. So that is malonic acid from, if you remember the Ohm's-Ga, then that's coming from the malonic acid. So I'm calling it malonate. Malonic acid, recall. So I'm going to drop the ic acid, it becomes malonate. And what's past the oxygen is a methyl group. So rather than calling it methyl-methyl malonate, I call it dimethyl malonate. I could also call this, since if let's say we had C double bond O, C double bond O, we have an ester, we have a methyl group. On the other side, we have an ethyl group. So there are 2 different groups. It's asymmetric, right? It's a diester and it's asymmetric. Then on one side, I say that I have the methyl group. On the other side, I have the ethyl group. So I'm just going to call it ethyl-methyl malonate. And that would be the name of that. So just put the R group past the oxygen on each side, which is the alcoholic part, and end it in an 8, and that gives you the name of the ester. If you look at the last one, here's my ester past the oxygen. I have my T-butyl group, so it becomes T-butyl cyclohexane carboxylate. If you were to provide the name of this, I would call it acetate. So that means it's supposed to be a 2-carbon chain. Propyl past the oxygen, that means it should be a 3-carbon chain. So I have 3 carbons connected to an oxygen, which is connected to an acyl. So again, what's at the last part of the name is your carboxylic acid end of the ester. Acid end of the ester. And what is in the prior, in the initial part of the name, that is going to be your alcoholic end. Alcoholic end. If I look at the next one, ethyl propanoate, that's just the reverse of what we just drew. That's propanoate. And ethyl means that 2 carbons are going to follow the oxygen. So again, propanoate comes from the propanoic acid, and ethyl is what is going to follow past the oxygen. Don't forget to put in, a lot of times I find students forget to put in this oxygen. That means it will be a ketone. So keep that in mind. It will be a different functionality. This is stemming from a cyclohexane carboxylic acid. So let's name that first. Cyclohexane carboxylate. And past the oxygen, I have an ethyl group. So the name becomes ethyl cyclohexane carboxylate. All right, so like I said, carboxylic acid derivatives will have an acyl carbon, which contains that Y group that you can have that leave, and you can have the reaction with the nucleophile such that the nucleophile adds on and Y gets substituted. And so I'm just basically giving you a moment to recall for yourself. You should be finishing up this reaction, so pause me and write down the sp3 hybridized intermediate yourself. And that's what you should get. That's your substitution. Hence, we also sometimes call it the nucleophilic acyl substitution. This is not your SN2 or SN1 reaction. This does not go through kicking in. You can't put in, if you are thinking that, oh, this is just looks like substitution, so it must be SN1 or SN2. And if you're thinking that you're going to bring in your nucleophile attack and Y leaves, bad idea. That's 0 points. Because again, recall from organic 1, you cannot carry out an SN2 type reaction on an sp2 hybridized carbon atom. This particular nucleophile has to come in a specific bond angle for the reaction to take place. Your sp2 center is completely planar. Attack takes place from the nucleophile from top or bottom, and then it goes through. You do have to form this sp3 hybridized intermediate, and then your leaving group is expelled to generate a new carboxyl compound, which leads to the substitution. Okay, so keep that in mind. Now you may ask a question if certain nucleophiles are more reactive to this than others, and that's a very valid question. So for example, if you were to compare perhaps your alpha position completely containing like many R groups, and these R groups could be hindered, could be methyl group, right? So it's a T-butyl group that you have. That will be least reactive because there's a lot of steric hindrance that you're going to get from there. On the other hand, if you consider one in which you have only hydrogen, so there is basically no hindrance that is offered or induction that is offered by that alkyl group, then the C double bond O is very available. And if it is very available, your nucleophile can attack really readily and your reaction will work like a charm. You are going to end up with your product easily. So in terms of rate of reaction, if you have this as a T-butyl group versus perhaps isopropyl group versus perhaps an ethyl group, so let's call it ET, and maybe a methyl group, methyl is going to be the easiest. And if you had a hydrogen, that will be, of course, the best, just on the basis of the sterics of that. But sometimes that C double bond O could be controlled by the electronics as well. So for example, if you had just that C double bond O connected to a Cl, maybe it's a CH3, you have that C double bond O connected to an anhydride, you have that connected to an ester, you have that connected to an amide. So all of these are the R group is the same. All of them are methyls. And what's different is essentially the leaving group, right? The leaving group is different. So again, I can't emphasize enough, if you ask that question, what's different? That helps you in analyzing these things much better. And it's not rocket science, it's common sense. Ask that question. That will enable you to move forth with it. So if you want to carry out a nucleophilic acyl substitution, what should you bring in? You should bring in the same nucleophile. You should bring in the same nucleophile at each of these centers. One could say that if chlorine readily leaves, then that reaction should be very fast, right? So how can you connect to this? Absolutely, if you're thinking leaving group capability of each of these, you're on the right track, absolutely. So let's take a minute to write down the corresponding conjugate bases. We have HCl in case of the first one, acid chloride. We have acetic acid for the second one. We have methanol for the third one. and we have NH3, ammonia, for the fourth one. So what do you think is the leaving group capability? The rule is stronger is the conjugate acid, better is the leaving group capability, right? So that's the order that we have. And your HCl is the best acid. That means the Cl is the best leaving group. So this is going to be, if I were to order them as 4, 3, 2, 1, I would say the highest number being the best or the fastest. That will be 4, followed by 3, followed by methanol, followed by the amide. And that kind of makes sense if you think about it, because we contain different kind of proteins. We contain structural proteins, for example, in our skin. And if you were to take a shower, right, because water is a nucleophile, so if you consider H2O and you consider the same H2O on the acid chloride, we have said that that water can hydrolyze that HCOCl. On the other hand, if you were to attack that on the amide, that reaction is not going to just work just like that. So if it's not that if you stepped into your shower and came out, some of that protein got denatured by taking a shower, right? That will be weird. So yeah, our proteins are pretty stable at room temperature. Thank goodness for small mercies. So you can always connect the idea to your daily life as well. Okay, now that we have seen essentially all of our carboxylic acid derivatives, I want to give you a quick look again as to which one is most reactive. We identified that it'll be acid chloride. So this picture is a great way to think about what our possibilities are. So this is kind of like that cascade. So you can convert an acid chloride into the anhydride. You can convert that into a thioester, into an ester, as well as an amide. But the reverse is not true. That means you can't just go from an amide and convert it into an acid chloride. So water can only fall down. Higher it is, more reactive it is, and it can be converted into the more stable form of the carboxylic acid derivatives, not the other way around. So to show you that, I have always considered carboxylic acids as the central sort of go-to, if you will, that you can use for reactivity. So over here I have for you the cascade as well as the reactivity. I just called the carboxylic acid as somewhat like a grand central in terms of reactivity. That means all of your functionalities, they can be converted by a simple hydrolysis reaction. Hydrolysis meaning lysing using water. So breaking up of the COOR linkage into the OR linkage into the corresponding OH. You can do that from either the amide, you can do that from the ester, from the anhydride, or the acid chloride. It's fastest with the acid chloride, not so much in case of the anhydride. That's a room temperature reaction, but both your reaction with the ester as well as the amide, that requires heat, or it may be a slow prolonged reaction that will require some time. Or it might have to be acid or base mediated. But notice how this picture essentially shows you how you can convert the acid chloride into the anhydride. You can convert both the anhydride as well as the chloride into the ester. And finally, you can convert the acid chloride into the amide. You can convert the ester into the amide. You can also convert the anhydride into the amide. But the reverse reaction, that means going up the cascade, up the hill, is not possible. So keep that in mind as we go and further dwell into what are the various reactions that we can consider. So this is a great point to stop, and I'm going to then discuss the reactivity and the methods of preparation of all of the carboxylic acids and what are the interconversions that we need to think about as we go forward.